Hello everyone, welcome to the INQA seminar series. Today we welcome Shuvro Chowdhury who's currently at UCSB. Please start.
Okay. So thank you, Eugene, for the introduction. Hello, everyone. I am Shuvro Chowdhury from University of California, Santa Barbara. I welcome you all to my today's talk, Accelerated Quantum Monte Carlo with Probabilistic Computers. So let's start. So the mainstream computing today is dominated by two major computing paradigms. The day-to-day devices that we use in our, let's say, desktop, laptops, smartphones is based on digital computing. And in digital computing, the basic computational unit is called a bit, which can have two possible states, either in logic 1 or in logic 0. Now, the other major computing paradigm is quantum computing, where the basic computational unit is called a quantum bit or a qubit. So like a bit, a qubit can also be in logic 0 state and logic 1 state. But in the case of qubit, they are also allowed to be in a state which are like superpositions of 0 and 1. And that kind of like makes quantum computing very interesting. And now we are seeing that many tech companies are like investing heavily on quantum computing. But we now live in an era of machine learning and artificial intelligence. So these sharp rise in machine learning and artificial intelligence, and also the requirement from verification of quantum algorithms and quantum circuits, pose a significant computing and energy demands. And that's why we're also seeing the rise of physics-inspired devices and domain-specific hardware. So today, I'm going to talk about such a domain-specific computing paradigm, which we call probabilistic computing or p-computing. And it is based on an idea of a probabilistic bit or p-bit in short. So like p-bits are also like, can have two possible states, logic 1 and logic 0. But unlike the bits, p-bit can continuously fluctuate between 1 and 0. And p-bit is a classical and robust quantity. It can operate at room temperature, and it can be fabricated using existing technologies. So that's why we are kind of like interested about this p-bit and probabilistic computing. So, what are the possible application area of p-computing? So over the years, we have identified a lot of applications for probabilistic computing. So one major area of application is optimization, but not necessarily limited to Ising or Kubo type optimization. It can be generalized to non-Ising or Kubo type optimization too. I have put down some references. If you're interested, you can take a look. And then today, mostly I'll be talking about this quantum emulation with p-bits, and we have recently published a paper on this. And then one important application of p-bit is like this massively parallel random number generation. If you want to generate a lot of random numbers in parallel, then p-bit can be very efficient to do that, and it will do that for you with very low cost. And recently, we are also analyzing the applicability of p-bits in machine learning, both in classical energy-based model and belief networks, and also for learning the quantum systems with machine learning techniques. So these are kind of like the three broad categories of application for p-bits that we are kind of like investigating. So now let me tell you about what a p-bit is actually. So a p-bit is a three-terminal device where it has a real valued input, and then it has a binary or like a two-valued output. And the third terminal is the power terminal. Now, the ideal behavior of a p-bit should be like this. Like if you apply a zero input to its input terminal, then it should spend half of its time to the +1 state and half of its time to the minus state. -1 state. So equally, it should be equally probable, both states. But if you apply a negative input to its terminal, it will stay in the -1 state more time than it will be on the +1 state. Now, you can do the opposite thing also. If you apply a positive input, then it will stay on the +1 state more than the -1 state. And mathematically, we can idealize these characteristics using this equation. And in the context of machine learning, it is well known, this equation is well known as binary stochastic neuron. So now, how can you build this equation in a hardware? There are many possibilities. You can use nanomagnet-based devices such as MTJs, or you can use Ginard diodes and nickelates, something like that. And then you can also use, you can also realize this pivot equation in digital CMOS, and you can just mix and match. You can have some nano device things and some digital things, so you can have a mixed signal CMOS also. Now, in order to give you an idea that how a hardware pivot can be useful, so let's say we want to emulate this thing in a hardware, in order to realize this equation in hardware. So one possibility is that you can use, for this R, which is a random number, you can use a cheap random number generator, like for example, linear feedback shift register. And then it will, in order to do that in hardware, it will take you like these thousands of transistors. And if you want to realize the p-bit whole as a whole, then you have to add this lookup table and comparator, everything for this equation. And this will cost you even more transistor. And if you want to go to for higher quality random numbers, because in many, we have seen that in many possible applications, you need higher quality random numbers, and then it will cost you even more. This is like around 11,000 transistors per p-bit. But if you can use these nanomagnet-based devices for a p-bit, then you will you can just get away with just 4 transistors plus a MTJ or a Ginard diode, something like that. And in terms of energy, if you look at this, then also, so in terms of energy, when you use low quality RNG, they are also kind of like giving you consuming more energy than a nanomagnet based or SMTJ based pivot. So this is like kind of like 2 femtojoule compared to like 145 femtojoule. And this is all just a pivot. So if you have an application where you need like 1 million pivots, then that's already a 10 billion transistors only for the pivots. But in order to make things work, you need to interconnect the pivots and everything. That is not included here. So that's how you can see that if you can realize these pivots in compact hardware, that can save you a lot. So this is all about pivots. Now, you cannot solve any problem with just a single pivot, right? You have to kind of like have an interconnected network of pivots. So the p-computing equations are given by this, like each pivot in an interconnected network of p-computer kind of like iteratively solve these 2 equations. And this choice of input kind of like comes from this Ising energy model, but it is not necessary to have this Ising energy model for a p-computer. You can have any energy function. On the only condition is that it has to be kind of like easily realizable in a hardware. So if that is possible, then you can just replace this energy input equation corresponding to your energy. And then if you use these equations and let the system go for a reasonable amount of time, then the computer will follow this Boltzmann law, where it says that it will visit the states based on the energy negative exponential of the energy of that particular state. And like the pivot, you have many options for building the synapse also. You can use analog circuits like crossbar arrays, memristors. You can also use digital CMOS, and any suitable hardware that you might want. So this is kind of like brief overview of a p-computer. And our vision is like to build a asynchronous p-compute interacting network, like and inspired from this nature. Like in nature, you have these asynchronously interacting bodies, and these molecules or these particles, they act locally, and they do not require a clock or any synchronizer. So we want to build a p-computer where the p-computers will be locally connected, and they will work asynchronously. They will not depend on a synchronizer or any clock. And this idea of this p-computer was actually inspired from Feynman's quote that where he said that if you want to build a simulator for a probabilistic nature, then you should build a computer in which the computing in itself is inherently probabilistic. So that's where the idea was generated. Now, one important idea of this p-computing is that its performance, which is usually measured in flips per second or flips per nanosecond, kind of like increases with the ability to incorporate the number of qubits in your chip. If we can incorporate more qubits, it will grow linearly, the performance. So with this brief introduction, I will now move on to this second part of my talk, that is like our recent publication on quantum simulation with qubits. So in 2021, King et al. Published this paper in Nature. And what they basically did is something follows. Like they took a 2D square octagonal lattice and they applied a transverse field Ising Hamiltonian on this lattice. And they emulated this system in their quantum annealing processor. And they also did the same thing on a CPU with path and integral Monte Carlo code. And they kind of like reported that for a given particular transverse field and a particular temperature, the equilibration time in their quantum annealing processor was like 3 million times faster than an optimized path integral Monte Carlo code on a CPU. And then, yeah, if you kind of like plot their data, so then you can see that the CPU code is kind of like going roughly in n squared. But I just want to be cautious here that this is just only 4 data points, so it may not be very conclusive. But it looks like that it's going n squared, and they are kind of like their quantum annealing data kind of like going like roughly square root of n. So they were kind of like seeing an scaling advantage too. Okay, so then we kind of like thought that, okay, this was for CPU, but what about if we include this domain specific hardware like p computers? What will happen to them? So will our p computer give a scaling advantage, or it will provide a hardware acceleration? And it is well known that transverse field Ising model is a stochastic problem, so there is no sign problem in it. So it should be possible to get some acceleration with domain-specific hardware like p computers, which is based on classical quantities. Qubits are qubits are classical quantities; they are not quantum. So since TFIM is a stochastic problem, we expect that qubit should be applicable there, and they should be able to give some sort of a scaling advantage or like prefactor acceleration. So that's what that is what was kind of like our thought at that time. And so our approach was something like this. We took their 2D square octagonal lattice. We applied transverse field Ising Hamiltonian. And in our case, we applied the Suzuki-Trotter transformation. So we have many replicas of the original system. And we used 10 replicas in our whole analysis. And so that our trotterization error is like minimal. So, and then what we did is like we applied graph coloring to this whole replicated network, and we found that we can use just 2 colors for this replicated network. And for this replicated network system, we then put this replicated network in Amazon AWS Web Services FPGA. And in a FPGA, we have designed an architecture where each color group of qubits can be updated in a single clock period. So in this problem, we have 2 colors, so we can complete a sweep in just 2 clock periods. And with this architecture, we are able to kind of run this system with 8 nanosecond clock period. So in order to complete one single sweep, we needed 16 nanoseconds. So with this principle, so we kind of like started from exactly same initial condition that King et al. Was using. And we observe the same order parameter, which is defined here. So, and then we started from this initial condition, and we kind of like let it go. Like from there, we just let it go. And then we see that after several thousands of sweeps, it kind of like saturates and goes to a thermal equilibrium value. And then we use the same criterion that King et al. Used to define this convergence. So this was like how many samples it takes to reach 95% of 95% of the equilibrium value. So we get the saturation value, we take the 95% of it, and we look at the number of samples that is required to get that point, and then we just multiply this number of samples with 16 nanoseconds based on the architecture we have, and that's how we get this purple curve, which is like our graph colored P computer curve based on a FPGA based simulation. And this is kind of like I just want to make the point that this particular point on the left hand side was like actual FPGA simulation, actual FPGA realization, but the other points, 3 points, were kind of like projected from this principle that we collect this a number of samples from running the problem in the MATLAB. We get the number of samples required for the convergence, and then we multiply by 16 nanosecond, because in our FPGA we did not have all those resources to run these things. But our principle is general, so we should be able to do this thing repeatedly given the resources. So after doing this, we immediately see that our P computing approach gives roughly a 2000x improvement over this optimized cluster algorithm that King et al. Did on CPU. And scaling wise, we also see that we have roughly a linear scaling with the problem size. And here I want to mention another point, that this scaling improvement is coming not from the algorithmic side, it is coming from the massive parallelism, that in our P computing system we can parallelize all these P bits in a hardware sense. So that's how like in our architecture we are kind of like updating n by 2 P bits for this example at a single clock period. So that kind of like takes one n away from this n square, and that's how it is becoming n. So that's the point I wanted to make clear. Okay. So we have seen that, okay, with our digital approach of the P computing, we can get 2000x improvement, but then it is still not there. Like the quantum annealing processor was still 1000x, roughly 1000x better than our digital emulation. So we kind of like thought that what can we do to make it even better, or is it the end? So one inspiration was like, okay, so if we do not use a clock, like what happens if we follow the nature? In natural processes, we do not need any clock. So we wanted to go and see like what a clockless or autonomous structure can do to this problem. And that's why we bring in these nanomagnet based devices. And that's why we do another simple example to get the idea, like how much improvement can we have. So we do a classical version of the original problem and on a smaller scale, because this is done in SPICE, so it kind of like takes days even for this small scale problem. And we used a previously studied and experimentally benchmarked model for this pivot. And we also used a physics inspired synapse, which is like this resistive network, to solve this 6x6 classical triangular lattice, which consists of 36 pivots. And we repeat the same problem in our digital approach also. And in this case, I just want to mention that this problem has 3 colors because of this triangular nature. So we simulate this same problem in our pivot approach based on the nanomagnet devices, and we repeat the same problem on our digital approach on a FPGA, and then we kind of like see these results. Like we kind of try to match like this SPICE result and this digital approach with graph coloring, and we see that like for this example, SPICE kind of like converges to this problem in 5.15 nanosecond, whereas this graph color requires 72 samples to converge, And if we do an equivalence, then it kind of looks like this in order to match this FPGA result with our nanomagnet based device SPICE result, the FPGA must run at a clock period which is like roughly around 20 or 24 picoseconds. So which is like very fast compared to the modern standard, usual standard. So that is kind of like we start when we did our digital simulation, we had a clock like 8 nanosecond, clock period of 8 nanosecond. And then this principle, this nanomagnet based asynchronous principle allows us to run these things in 24 picoseconds. That's why we get kind of like get another 2 orders of magnitude improvement. And that was kind of like our projection. Like if we do nanomagnet based device and really physics inspired synapses, then we can go down up to like this. And that's what we reported in our latest publication in communication physics. But and then we still have a little bit of gap, like this is like around an order or so. And this is where we are not clear that if we can do better or it is like really something that is coming from quantum algorithm. But that's for future research. But before ending this, I just want to mention that this acceleration that happened with this P computer was made possible because of these two key things, which is like massive parallelism, that we have very compact P bits so that we can lay out many P bits in parallel in a hardware, and because of this autonomous clockless principle, like we are running things asynchronously, no one needs a clock to synchronize them. So this is my last slide where I also compared like this P-bit approach with the state-of-the-art devices except for the CPU. Like here I'm comparing the results with GPU and TPU, and all of these results are based on like two colorable problems. So you can see that on the x-axis I am plotting the throughput in flips per nanosecond, and on the y-axis I am plotting this power consumption in watt. And you can see this state-of-the-art devices are like on the left-hand side of the plot where you have low sampling throughput and high power consumption. But the all digital FPGA simulation that I did and our colleagues are doing kind of like gives us like a sampling throughput at a very low cost. And research are going on, and we have already seen publications that shows that SMTJ based nanomagnet based devices are capable of showing nanosecond fluctuation, and it has independently verified by many groups. And if we can use these nanomagnet based devices, and we can build a real P computer with like for example 1 million of such P bits, then we can have much larger sampling throughput at a very reasonable cost. Like our usual computing chips have like this power budget like of 20 watt. So within that power budget, we can also have this enormous sampling throughput. So that will be all for me, and thank you very much for joining. And if you have any questions, I will be happy to answer them. And if you want to follow up, you can please email me at this email address. So thank you very much.
Thank you for this talk. It's very interesting. Are there any questions?
Hello, I have a question.
Yeah, go ahead, please.
So this is I think that this is kind of the algorithm on a neuromorphic chip, right?
Right.
Yeah. So my question is, can you run this algorithm on the neuromorphic chip, which is, if I'm correct, the IBM they are developing such kind of devices. So I don't know if it's already available or not. But in hopefully near future, some IT vendors release such kind of neuromorphic chip.
Mhm.
In that time, so your algorithm will run on those chips, right?
Yes, yes. But just I want to mention that we are not developing any new algorithm. We are just taking like original a simple algorithm. Like if the graph coloring example algorithm that we are using, that is even worse on CPU compared to this optimized cluster algorithm. We are using the single flip Monte Carlo. If you really want to compare this on CPU, then it will be like just single flip Monte Carlo algorithm that is being translated into a hardware. So if you compare to this original algorithm to this thing, then advantage is even bigger. So that's why I was kind of like saying that this final projection that could have been a little bit smaller if we could use like this sophisticated algorithm for the P computer. So that's why I kind of like said that it is not clear to us that whether this gap could be even further reduced.
Okay, see. And what is the limitation of this implementation? So can you, for example, deal with a model with sign problems?
Yes, that is a very good question. So qubits are classical quantities. So they do not have any quantum like properties like this entanglement and superposition. So we are not sure at this moment that we can do. I mean, if we can solve this sign problem, then it is a Nobel Prize thing, right? So yeah, if we can do quantum problems with qubits and still have some scaling advantage, so that would be groundbreaking. But it is kind of like hard to achieve. And I mean, it requires enormous research. But at this point, even if our thinking is that even if we cannot break it algorithmically, probably we can give it some hardware acceleration, like prefactor acceleration for this sign problem related problems also. At this point, that's our best hope at this point.
Thank you.
Okay, these are very good questions. Thank you.
All right, I also had a few questions.
Yeah, please go ahead.
So I guess the simplest question is that it's not clear to me from this short introduction that you gave us how much control would one have over this device. As in, so I assume that the FPGA is relatively flexible, but does it mean that you need to fabricate a specific architecture every time? So you need to pay money for a new FPGA pretty much every time you need to study a new model?
Yeah, I mean, in this case, what we did is like we were kind of like trying to see the limit of the classical computing power. Like even, I mean, we are kind of like assume that let's give classical computing all possible flexibilities that we can give. So we are kind of like trying to find what is the actual difference between quantum and classical. So that's why we are kind of like doing not programmable things. I mean, a specific synthesize. But in general, if you want to do this, yeah, the best approach would be like having something programmable and kind of like a general kind of like architecture that is kind of like capable of mapping many other problems into a single synthesis. But in this case, we did not do that. We have a particular architecture.
Yeah, so from the point of view of quantum annealing community, so this paper is not actually the main claim that D-Wave has right now for the advantage. So the claim that they have is for the non-equilibrium simulations, actually. So, and I think they are pushing for that claim a little bit more. And in a sense that, and that claim is kind of, it's more fundamental. So even if you do quantum Monte Carlo perfectly, what they try to say is that their device does something fundamentally differently from quantum Monte Carlo. But if we ignore those debates for a second, right? So I'm interested if one would be able, using the controls that are realistic for this kind of chips, to do some sort of non-equilibrium dynamics experiments, not just the equilibration.
Okay, I see.
So yeah, that's one thing that I wanted to say, and another. So it's not super clear to me how those benchmarks on a classical CPU were done. But essentially,
So
there are
for
two
the
components.
classical CPU benchmarking,
Yeah,
we just took their data. We didn't do it
yeah,
ourselves.
yeah. But the thing is, right? Earlier you compared this p bits to the classical random generation, right? Randomness generation. So what I'm curious about, if you split the classical algorithm into two parts, which is one is something where you pre-generate all the random bits you need, and the second is your actual algorithm, and you just have some sort of a fast communication channel that feeds in the random bits as soon as you need them. So what would be the actual relative contribution to the computational time and computational power that those two parts will need for this quantum Monte Carlo computation?
This is a good idea, but yeah, good point. Yeah, but I'm not very sure about that. How to do that in it? I mean, yeah, I have to make a clear comment on that. But yes, it certainly looks plausible, and yeah, we should probably look into that also. Yeah.
Because if you could separate it into just a very cheap randomness generator and then use your normal digital computers for everything else, that would be easier than fabricating the specialized chips, I suppose.
Right, that's also a very good point. But in this case, what I have seen that in this particular problem, you actually cannot get away with cheap random numbers. Like I was trying to use this LFSR because at some point we are kind of like trying to see like whether we can also do these instances. And the idea was like, okay, I was doing Zoshiro, a high precision random number generator. So okay, let's reduce this with from Zoshiro to LFSR, and then I was seeing that I was not getting correct results. So for this particular problem, at least, you need high quality random numbers. So you cannot get away with cheap random numbers in this case. But yeah, in many other problems you might.
I see. Okay, that's all of my questions. If there's any audience questions remaining, otherwise, thank you so much for a very insightful talk, and see you all next week.
Okay, thank you very much.